What if I told you the secret to building way smarter AI wasn't about making them more and more complicated, but actually about making them simpler? Today, we're diving into a really clever idea from AI legend Geoffrey Hinton, and it all boils down to one simple, powerful rule. The shortest message wins. So let's just start with a kind of weird question. Can an AI actually be too smart? I mean, it sounds wrong, doesn't it? But imagine a student who's studying for a huge exam. Instead of learning the material, they just memorize every single practice question and answer, word for word. Well, what happens when they get a question they've never seen before? Total disaster, right? They just freeze? Well, that's a massive problem in AI. So you've got these two paths an AI can go down. On the left, you've got that student who just memorizes everything. In AI, we call this overfitting. The model looks like an absolute genius on all the stuff it's already seen, but it's fragile. The second it sees something new, it breaks. But on the right, that's our goal. That's real learning, or generalization. The model actually understands the deep down patterns, so it can handle new stuff, no problem. The big question then is, how do we push our AI to be the student that actually learns, not the one that just crams? And that brings us right to the heart of the matter, this overfitting problem. It's what happens when a model gets so complicated that it starts memorizing every little weird quirk and bit of noise in its training data, instead of the real underlying pattern. You know, early AI researchers knew this was a huge issue. They had to figure out some way to stop their models from getting too clever for their own good and force them to stay simple. For a long time, the solutions were kind of like using a sledgehammer. You know, they try things like just limiting the number of connections inside the model's brain, or forcing a bunch of connections to have the exact same value. Another common trick was something called weight decay, which is basically just punishing the model anytime one of its numbers got too big. And look, these things work, but they're not exactly elegant. Hinton and his colleague, Drew Van Camp, thought there had to be a better way. And this is where things get really, really cool. Instead of just penalizing complexity, they decided to reframe the entire challenge. They turned it into a communication puzzle. And to solve it, they borrowed this powerful idea from a totally different field, information theory, called the minimum description length principle. Basically, the best explanation is almost always the shortest one. But here's the twist. The minimum description length principle, or MDL, says the best model isn't just the one that gets the most answers right. No, it's the one that gives you the shortest possible message to describe two things. First, you have to describe the model itself, like its instruction manual. And second, you have to describe all the mistakes the model still makes. The total length of that combined message is what you're trying to shrink. Okay, let's make this into a game to make it super clear. Imagine you've got a sender who has a bunch of data. The sender's job is to train a model to understand that data. Then they have to send a message to a receiver that allows the receiver to perfectly reconstruct the original data. That message has to have two parts, the model's recipe and a list of all its mistakes. And the goal of the game, the only rule, is to make that total message, the recipe plus the mistakes, as short as you possibly can. So if that's the goal, how in the world do you make the message shorter? Well, this is the genius part. The secret is to be a little bit fuzzy, to be intentionally imprecise. The trick is to use what the paper calls noisy weights to make your description way, way shorter. Think about it like this. If you need to describe a number like -1.415926535, that takes a lot of information, a lot of data, a lot of bits. It's a very long and expensive message. But what if you could just say, it's around -1.4, whichever take a little. Suddenly, describing that fuzzy range, that sort of cloud of possibilities, is way cheaper. It's a much shorter message. And this isn't just me saying it. As Hinton and Van Camp wrote in the paper, it's just plain more economical. If you can wiggle a number a little bit and it doesn't really change the final answer, then why on earth would you waste all that precious information describing it down to the last decimal place? Being imprecise actually becomes a tool for being more efficient. Okay, so this is the part where things get a little mind-bending, so stick with me. You'd think that adding fuzziness or noise would just add randomness and make things more complicated, but there's this amazing counterintuitive magic trick at the heart of this whole idea that lets you actually get that information back. They literally call it the bits back argument. So let's walk through this magic trick. Step 1. The sender sends that cheap, fuzzy, imprecise recipe, along with a list of the model's errors, over to the receiver. That's our initial short message. Now, step 2. The receiver takes the output from that fuzzy model and just applies the list of corrections. And boom, they now have the perfectly reconstructed, 100% correct data. Simple enough. And here is where it gets really clever. Step 3. Since the receiver now has the exact same data that the sender started with, they can run the exact same learning algorithm on it. They can perfectly recreate everything the sender just did. And that means the receiver can figure out the exact same fuzzy probability cloud for every single weight that the sender used. The receiver knows exactly how much fuzziness the sender decided to use for every connection in the network. And that is the punchline. That noise the sender used, it's not actually random to the receiver anymore because the receiver can calculate it perfectly. So all the information, all the bits the sender sent to describe that fuzziness gets refunded. It's like the cost is zero. It's like sending a coded message where the key to unlocking the code is hidden inside the message itself, and it makes the true cost of communication unbelievably small. Okay, that is a beautiful, elegant, mind-bending piece of theory, for sure. But does it actually work? Does this clever bits-back idea actually make better models in the real world? Well, let's take a look at the results. And wow, just check this out. Look what the model did completely on its own. On the left are the final connection strings, the weights in the network. And you can see they've automatically clumped together into these nice, simple groups. And on the right, that's the simple recipe the model learned to describe those groups. It found this beautifully simple structure because the whole game was rigged to reward simplicity from the start. Now for the numbers. The researchers tested this on a seriously hard problem that had very little training data, which is like a classic recipe for overfitting. And their method got a relative error of just 0.286 on the data it had never seen before. And just to be clear, for error, lower is always better. And that is a fantastic score. And this chart really tells the whole story. Look, if you do nothing and just let the model overfit, you get a terrible error of almost 1. The standard method, weight decay, brings that way down to 0.317, which is pretty good. But Hinton's new method, the one based on sending the shortest message, is even better. It wins, clocking in at 0.286. It's proof that this really elegant theory actually delivers the goods in the real world. So in the end, this whole thing kind of forces a shift in how we think about AI. Maybe the goal shouldn't be to just build the biggest, most complicated model we can. Maybe the real goal is to find the simplest model that can still effectively explain the world. This idea that simplicity isn't just nice to look at, but is actually a powerful weapon for making AI smarter, is a lesson that is still shaping AI research to this day. And it makes you wonder, what other huge problems could we solve just by asking, what's the shortest, simplest way to explain this?